Hi, I'm Keishi Okazaki from JAMSTEC. First of all, thank you very much for inviting me such kind of very nice workshop. So today I'm going to talk on the experimental investigation of dehydration weakening and embrittlement of hydrous minerals and how it relates to intermediate depth earthquakes. So today we have so many nice talks, so probably I don't need to explain the background too much. And then my talk is kind of similar to what Nicola has, but more focused on what happened during the dehydration reaction. So first of all, I'm going to show natural example what happened at the subduction zone. So these are two end members of subduction zone. So top one is a kind of VP-VS ratio as cold subduction zone, and the bottom part showing the VP-VS ratio at hot subduction zone. So these are two end members. At cold subduction zone, as you know, so we have double seismic zone, and what top zone locate in the subducting oceanic crust, and then bottom one locate within the mantle, way deeper than plate boundary. On the other hand, at hot subduction zone, we have it's kind of extreme end member at hot subduction zone. For example, here's Nankai subduction zone. That's both in Japan, but it's very different. This is what I'd like to say. And Cascadia is same, actually, almost same. And then as hot subduction zone, we have just single seismic zone. And then but we have these pink dots show hypocenter of slow earthquakes. So we have at cold subduction zone we have double seismic zones, but we don't have any deep slow earthquakes somewhere around here. But at hot subduction zone we have slow earthquakes, deep slow earthquakes here, and then we have single seismic zone. So if you plot distribution of these intermediate depth earthquakes, it's like this. So vertical axis is depth below Moho. So this means here's Moho. And then horizontal axis shows number of earthquakes, intermediate depth or intra-slab earthquakes. At cold subduction zone, we have double peaks. And then one locate within the oceanic crust, and the other locate within the mantle. On the other hand, at hot subduction zone, we have single peak, and these peaks locate exactly on the Moho. So why it's different, even subduction zone, even in Japan? So the key is, especially if you focus on oceanic crust, the key is pressure, temperature, condition is very different. So this figure shows the pressure as a function of temperature, and these lines are showing the PT path of the subducting slab surface and Moho. So at cold subduction zone, we have these earthquakes, which PT condition is here, and then it's kind of related to lost night out reaction boundary. So if you lose lost night, so earthquakes disappear, it get quiet. It's consistent with the Bruno already showed this kind of data from Kita et al. And then as hot subduction zone, we cannot have actually lost night. Here, lost night out here, so we have episodes rather lost night. So we can say material is different at cold subduction zone and hot subduction zone in oceanic crust. So at cold subduction, we have lost night blue schist, and at hot subduction zone, episode green schist. So there's still recent research has kind of controversy because at high pressure experiment, anti-ride dehydration doesn't have any AE. Sometimes, but all the paper they have tons of AEs during anti-ride dehydration. So purpose of our studies let's test during deformation, real deformation experiment, and then so I can pick we got pick two kind of sample, end member sample. One is lost night, typical representative of oceanic crust material, and then antigolite is representative of mantle, hydrated mantle material. Of course, mechanism of intraslab seismicity is probably not there's so many ideas, not only dehydration embrittlement, but also I written very small, but shear instability or something like that. But this time I can test how dehydration and embrittlement work for these earthquakes. And I like experiments, so I run experiment in the lab. So I run experiment, kind of simple experiment. I put sample into the pressure vessel here, and the sandwich with strong material, and then shears, just sheared. But during shearing, we change temperature to induce dehydration reaction. So like for last night, we start experiment at 300 degrees C, and the pressure was 1 GPa, and during shearing, we change temperature with different speed from like 0.5 degrees C per second or 0.05 degrees per second. And then we also run same experiment using antiglide from 400 degrees C to 700 degrees C to induce dehydration reaction, like for last night, like from this condition to here, and see what happened during experiment. And then we also measure, not only we measure strength of the sample during experiment, but we also measured acoustic emission activity during experiment. Unfortunately, we have only single sensor, so we don't know where it's from. But we calibrate using during squeezing very soft material, aluminum metal, and then with same condition. So we change the temperature same as this experiment during aluminum metal deformation, because we use solid pressure medium apparatus. This means we have so many solid, it could crack during experiment, especially during temperature ramping. So we calibrate using very soft and then ductile material, how we have noise, and then how many we have acoustic emission from real sample. So these are typical results from deformation experiment. So vertical axis is differential stress, and horizontal axis is time after temperature ramping started. This means at initial stage of the deformation, we just simply apply the stress like this, and then at certain point, which is like 0 second, we change temperature to induce dehydration reaction. So both last night and antiglide, we have significant weakening during dehydration reaction. But this looks like a line, but actually it's dot each second. So during temperature ramping, so we have kind of fast sleep for last night because we have 1 point here. This means between here and here is just 1 second. We have kind of fast stress drop during dehydration reaction for last night, but it's kind of smooth for antiglide. This means we have slow weakening during antiglide dehydration. So let's take a look this part in detail. So it's like this. So it's for last night and antiglide, and this is acoustic emission during dehydration reaction. So vertical axis is differential stress, and horizontal axis is time after temperature ramping started. So for last night, so during temperature ramping, we have very teeny strengthening due to thermal expansion, and then start weakening and accelerate, and the fast sleep happen. So it's again, this is sampling rate was 1 second, so we have kind of fast sleep here, and then like this. We also record the fast sleep in displacement, this black line here. But for antiglide, we have kind of slow weakening like this. And then if you take a look acoustic emission, so for last night, we have many during dehydration reaction. But for antiglide, we have some. But to compare aluminum, so we have it's same, actually. This means most of acoustic emission for antiglide experiment is noise, just noise. But last night, we have significant acoustic emission during experiment. But we should note that so for structure is pretty similar. So this is recovered sample of last night. We have Y shear here, and then we have R1 shear here. So it's strains highly localized along one fault zone, actually. But for antiglide, we have similar structure during dehydration reaction, which is consistent with Brooks Proctor or Linda Charnock run. And then, so this means both are fault or both are brittle deformation during dehydration. But manner of sleep is very different. Last night is unstable, and then antiglide is kind of stable for sleep. So we use solid pressure medium apparatus for high pressure deformation. This means all sample are surrounded and solid material. So this could prohibit fast sleep. But if we assume like spring slider model, so like we have block and then pull with spring. So like if we have unstable sleep, so this unloading slope should be for the stiffness of the apparatus like this. And then if we have stable sleep, we have like this unload slope is shallower than apparatus stiffness like this. So we calculate the slope of each experiment, unloading slope each experiment. So we change the temperature ramping rate like this, like order of magnitude, but unloading slope during dehydration reaction is always same for last night experiment. But for anti-light, it's like always shallower than apparatus stiffness, which value is here. So we all have shallow unloading slope for anti-light experiment. So this figure shows kind of summary of unloading slope during dehydration reaction. So and the vertical horizontal axis is temperature ramp rate over strain rate, which is kind of temperature ramping rate showing like kind of dehydration speed, and then like strain rate is deformation speed. So if you like temperature ramp rate divided by strain rate, we can erase time dimension. So this means the time independent scale. So this means we can compare with natural subduction zone condition. For example, so somehow I had a movie, but it's gone. But anyway, so if you calculate that this scale in natural subduction zone, it's like 10 to 2 to 10 to 4. It's gray square, the gray box. And then our lab condition is 10 to 3 to 10 to 6. So our lab condition covers the natural subduction zone condition in terms of ramp rate over strain rate scale. So this means, and then for lost night, we always have unstable sleep. So this means in even natural subduction zone, we must have unstable sleep in lost night. But for anti-light, we have this kind of slope. This means the weakening rate is depending on the dehydration kinetics or like reaction rate. So this means we don't know what happened in subduction zone. And then one more problem is this unloading slope. So unloading slope in the lab or like apparatus which we use is 8.8 gigapascal per millimeter. But if you calculate this number in natural subduction zone, which is like just 2 MPa per millimeter, so like 10 to 3 orders of magnitude difference. So how can we overcome this difference is the next question. So now, so this is kind of funny because for rock squeezer, we design machine as strong as possible, or as stiff as possible, but now it's problems because we made very stiff apparatus, we cannot scale to natural condition. But we put just spring, but it's not like coil-like spring, but it's called beer washers, which I cannot pronounce it exactly, but we call dish spring or something like that. And then we can stack 8 dish springs here, and then we reduce stiffness of the machine, like 1/35 of the previous standard stiffness. So now it's 250 megapascal per millimeter. And then, so we run experiment using same experimental condition, but different stiffness. And then these are data. So these are our data with standard stiffness, and these are our data with compliance system. And then now we have all data follows the stiffness. The unloading slope is same as stiffness. But if you take a look data, so this one, so here's standard stiffness data, and here's more compliant stiffness data, but still it's stable sleep. So, but this is consistent with not only our group, but also like, he's here, but his recent report also they have, for anti-light dehydration, we have 14, but always stable sleep. But what if you use more compliant system, which is gas apparatus? So now we have more compliant system like 58 megapascal per millimeter. And then these data showing, so but problem is it's low pressure experiment. So we don't know pressure effect or stiffness effect, but result is very different. So if we, at 400 degrees C, we have just stable sliding. And at 650 degrees C, we have giant stick slip, like big sound, and then like many people next of the lab, they show up the lab, what happened, or explosion, or something like that. And then, but at intermediate temperature, we have like very small stick slip. So if we take a look in detail, so at intermediate temperature, we have slow stick slip, like stress level is pretty small, and then duration is kind of long. And then if you increase temperature, like this, we have giant. So its shape looks similar, but time is just 7 milliseconds. And then, so this behavior is not only temperature dependence, but also actually background sliding velocity here. So this figure shows temperature as a function of sliding velocity, and then what behavior we observed. So this figure shows not only temperature, so the slow stick slip or stick slip or stable sliding. So the sliding behavior is totally depending on not only this one, but also sliding velocity actually. So why? So it's kind of, I think, kind of simple model based on like his equation. So like unstable slip or slow stick slip happen when the stiffness is smaller than critical stiffness. And then critical stiffness is not elastic constant, but material constant based on like this. If dehydration weakening control this situation, we can write this kind of equation. And then what happens is like shear strength drop over like displacement is kind of a function of pulp pressure build-up rate over dt over dx. This is inverse of sliding speed, right? So this is kind of similar to what we use for scaling to natural subduction zone condition. And then if you like put some material constant based on dehydration kinetics from literature, we can make equation like this. So critical stiffness of the dehydration reaction plus friction behavior is something like this. So now I plot this as a function of like stiffness, this means elastic constant of apparatus or natural subduction zone fault zone. So this black line showing like 1-by-1 relation, so like K critical stiffness over stiffness is 1 is here. So and then if this number is high, like this region should be unstable slip, and at this region, if our data plotted at this region, this should be stable. And then this green shows stable slip. A condition we observe stable slip, and the blue shows intermediate slip or slow stick slip or slow weakening observed, and then red shows violent stick slip observed. And then vertical axis is stiffness. This means gas apparatus, which is compliant, more compliant system plotted here. So like we can explain our data based on this discussion. And then for Greek's experiment, which is very stiff experiment, stiff apparatus, we can plot only stable weakening or something like that. And then for recently, we have many people run experiment using D-dia. D-dia should be super stiff, like way over here. So that's why I'm not sure, but that's a reason why we couldn't observe like fast slip using D-dia. That's possible. And then this is case of antiglide. For lost night, we have like weakening. So this means that lost night data could plot somewhere away this region. So this is kind of, so what this is kind of dehydration controlled by dehydration kinetics and sliding speed or background strain rate. This means like kinetics is totally depending on the temperature. So if we have high temperature, and then if dehydration reaction goes faster. So this means this is pressure and temperature figure, and then this is boundary, stable boundary of antiglide. So at this intermediate pressure condition, kinetics should be faster because dehydration happens at high temperature. But if you go too high pressure, so dehydration temperature is kind of low, so kinetics is slow. So probably it can be stable weakening. And then I'm not sure what happened, but we could have slow slip or just regular earthquake at this region, like intermediate temperature condition. So this is summary of our talk. So like those night is surely unstable, even in subduction zone condition. But antiglide serpentine, not sure what happened at subduction zone. So we need to investigate more. That's it. Thank you very much.